is on. Okay, well, as I was asking, are there any questions about the homework assignment? How to get started? Okay, well, I'm gonna give you guys, a little bit more today. I'm hoping most of you still remember what we talked about on Tuesday. Okay, so we'll basically continue from that discussion. The lab portion was recorded now, with the voice. Yep. Question?
Microphone's on now?
Huh?
Microphone's on this app?
Microphone is, let's see. Yep, it's on.
Excellent.
It's getting recorded. Yep.
As you were.
It's good to check. It is good to check. All right. So let's go back to this class. And we'll go to the homework assignment. That was one issue with the homework assignment. And it is mostly, it has to do with the Makefile, so I'm going to explain what the problem is and how to solve that problem. I'm just getting back to the homework assignment, which is interface with C, C++. And I'm going to re-download the file because I don't think I unzipped it into a folder that is saved elsewhere. So let's see. It's called str and dcpy.tar.gz. Okay. All right. So one of the problems has to do with the Makefile. And I'm going to show you the Makefile. In the past, I have more time to talk about the Makefile, but with this semester, I shifted a lot more material to the earlier stuff, like how to design your own processor. So I don't have as much time to talk about the Makefile. But there are two things that is kind of important. The first one is when you implement your code in assembly and you don't want to use the C version anymore, you kind of have to comment out this one. Now you have several options, but commenting out this one is one way to do it. So you can use a pound sign to comment out this one, and assuming your assembly file is strdcpy.uppercase-s, you can add it to the ASRC or the assembly source macro or variable, and this should take care of the problem. But unfortunately, it does not. Okay, I'll show you guys what I mean by that. So I save the Makefile, exit from the editor, and I say make it clean first, okay? Because make clean will delete all the files that are actually generated by the compiler, and they're not really needed for submission, okay? So make clean is one way to make sure that your project starts clean as far as compiling is concerned, but it does not remove any source files. So if you have any source files, they should be safe. When you say make, it will show you exactly what it does in order to generate the executable, which is called main. But one thing you can see right now is on this line, it says GCC-00, no optimization, blah, blah, blah. But the most important part is it's still using the .c file. It is still using the C source file and not the assembly source file. The reason why this is the case has to do with this. Okay, so let me go back to the Makefile here. The Makefile it basically specifies dependencies. I do want you guys to understand the basic idea of what a Makefile is. It's basically giving you a list of dependencies, and then depending on what is updated, the make utility program will use the shortest route to bring everything up to date. That's basically the idea of a Makefile. It starts with the first rule. Okay, the first rule is the variable exe. To make that, it depends on these particular items. So what is exe? Exe is defined here to be just main. So the main executable depends on all of these items here. This one is kind of an advanced feature because it says it depends on CSRC, or the C source files, which would be this definition here. But this part of inside the parentheses basically says replace the .c extension with a .o extension. Okay? So instead of depending on main.c, the executable depends on main.o. ASRC now has strdcpy.uppercase-s, So now it would say, oh, change the dot uppercase S to dot O, and so on. CC source stands for C++ source file, and we don't have any, so that part remains empty. Okay, so from this rule, it basically translates to main, which is the target. This is called the target of what you're trying to make. Depends on main.o and also strdcpy.o. But do we have any rules to make the .o file? The answer is no. There's no rule to make the .o file. So in the absence of the .o file not having its own dependency, the compiler gets smart. And when the compiler gets smart, what it does is to say, well, let me see if you have source files that can be compiled into a .o or object file. And since we have both the .c and the .s version of a string D copy, it automatically picks up the .c file and not the assembly source file. So that's why it does not do what I wanted to do, because we have two source files that can both be used for this purpose. So that's the main reason why it is not working. So any questions at this point? Yep.
So what do we have to do to make it?
Okay, the easiest way to make it work is to rename the .c file so that the extension is not .c anymore. So you can say cbak, for C backup or something like that. As long as it is not a recognized extension, it will still be okay. I can see that there's another option to do this, but it will require changes to the Makefile. The .d files, okay, you can see that we have some .d files over here. The .d files are basically what we call the dependency files. These are generated as well. So these are generated .d files. So one thing we can potentially do is at the end here we have all of these includes, and they depend on all the .s changes into .d, the .c change into .d as well. So one thing we can potentially do here is to say, okay, if it's a dependency file from C, we call it CD. If it is CPP, we say CPPD. If it is S, it is SD. So now we will go back here and change those as well over here. And I think that will fix the problem. Okay? Because it's confusing, itself, and go like, okay, I need a .o file, but what do I do to make that? And you can see that we still have a string.c file, and it will picks it up and go like, oh, okay, I know how to generate a dependency file. So let me give this a try first, because I have never done this before. So we'll go ahead and see if this works. Okay, so save the file, make it clean again, and then do another make. It says no such file or directory. No such file or directory. Okay. I know exactly why, because when we create these, this rule, okay, where the cursor is, this is actually the command line to create the .d file. The .d extension is automatic, and as a result, it automatically makes a .d file and not a .cd file. And that's why there's no CD file. So when I try to include the .cd file, it failed. So the only other way to do this is to see if I can change the -m and -mf option to create a file of a particular name. All right. Let's see. So it basically created the .d files, but not the .sd or the .cd file. So main.d is still here. Let me show you what is main.d. This is main.d. Main.d is basically just saying, okay, the object file for main depends on main.c itself, which is the source file, but also the file that we are including into main.c, which is in this case a string d copy.h. And the magic about this whole thing is it can figure out the dependency of #include files automatically. So if you add a new #include into main.c, it picks it up, and you don't have to track all those header files. Okay, That's the quote-unquote magic part of this. But this is not working because the output of -mm is automatically .d. It doesn't know how to, okay, I don't have it here, so let's take a look here. GCC-mm is an option. Okay, so right here it explains the -mm, but the output mentioned only the user header files included using #include in double quotes. It does not include the system include files, which is what I want because I don't want it to be dependent on that. The question is, can I control the dependency file, the name of the dependency file? So dependency. Okay. Doesn't look like there's an option to do it. So the output is always named with a .d. The only way I can do this is to rename the file after it is generated. So one of these variable is actually the output, the target file. And if I look at this, no such file, no rule to make it. Oh, you know, well, I guess this won't fix it. So we'll just go with the easiest way to fix it for now, which is not to change the Makefile itself, but to change the name of the source file. So I will do that just after I get this fixed. Okay, so this one at least works. And then what we'll do is I'm going to show you how to create your source file. So the source file strdcpy.uppercase is nothing more than just a text file. So that part is fairly easy. .global, okay, don't forget the .global because otherwise the label string dcpy just string dcpy is not going to be available to the linker. So you got to have a .global first, and then you define the label, and just have a single return here. In other words, I'm defining a subroutine that doesn't do anything. Okay, it's just a little stub. Okay, because I just want to test to make sure that the make utility program is working. So now that I have this, I can say make it is main is up to date, make clean, and then make again, and you can see that it's still picking up .c file and not the assembly source file. So one way, the easiest way to fix this problem is to move the .c file into a file that has no extension or an extension that is not recognized. I just replace the the extension, with an underscore. Okay, so instead of strdcpy.c, it is now _c. And then make again, make clean, make again, and it is complaining. Okay, I have to remove the .d files manually first. So now this time it picked up main is up to date, make clean, make again. Okay, so this time it does pick up the assembly file because you can see it's now using the assembly source file and not the C source file anymore. Okay. Is that okay? Does everybody kind of understand what to do with this one? So to summarize in one sentence, rename, once you're ready, once you have written your assembly code and you want to switch to test your assembly code, change the strdcpy.c file to an underscore, instead of the dot, then do a make clean and remove the .d files manually, because otherwise it won't be able to make clean by itself. So you have to remove rm star.d, remove all the dependency files manually, do a make clean after that, and then do another make. So that will basically restart the whole thing. Is that okay so far? Okay, all right. All right. So from the lab of last time, we talked about how to use symbolic names to refer to individual items on the stack. Okay, to be more specific in the stack frame itself. So are there any questions about that part? No questions about that part? Any questions about strdcpy_c, which is the C code that you have to convert into assembly code? Any questions about this part? Oh, there was one more thing. How do we push a character on the stack? There was a question about that because we haven't really talked about, okay, we know how to push 32-bit items on the stack. We have an instruction to push 16-bit items on the stack. But source, okay, let me point out exactly where we are at here. Source, src, is a pointer to a character. So when you dereference source, it is a single character, but it is also being passed as a parameter to strc. So the question now is, how many bytes am I supposed to push on the stack? Now, do we know how to push 1 byte on the stack? The answer is yes, we know how to do it because we know how to not use the push instruction and instead use the add and move instructions to actually push something on the stack. So it is possible to push just 1 byte on the stack, but the more general question is, what if there are additional parameters? The way it is right now, it doesn't matter, okay? Because this is the second or the last parameter to call string char. So it doesn't matter whether you push 1 char, 2 bytes, or 4 bytes on the stack. Because of the little endian convention, the character or the 8-bit that you actually need is always at the same place. Is that making any sense? Okay, if you draw the stack, the call frame. So let's draw out the call frame here. We have the usual stuff. We have the return address, and then below that we have old EBP, and then right above return address is which parameter? What goes right on top of return address? The first argument or the second argument? The first argument, okay? The first argument has a lower address than the second argument. So that means in this case, vlim, which is a pointer to a null-terminated string of delimiters, is going to be here. So what about the character that we are trying to check? It's on top of this, right? Okay. So now the question is, okay, we know this is a character, which means it only takes up 1 byte. The question is, what if I push 4 bytes on the stack? Would it mess up anything? Well, it depends on whether the processor is little endian or big endian. If it's little endian, where is the byte that we are actually pushing? So let's just say that EAX has the character. Okay, take it back. So let's just say that AL, register AL actually has the character that you want to push. This is the only thing that matters to the subroutine. But instead of pushing, there's no such thing as push byte AL, okay? That doesn't work. So instead of using push byte, what if you use a push long instruction, and instead of pushing AL, which is 8-bit wide, you're now pushing EAX, which is 32-bit wide. Would that mess up anything? The answer is no, it's not going to mess up anything, because when you push 4 bytes on the stack, where is the character within these 4 bytes? It's the first one out of the 4, which is this one here. What happens when you push 2 bytes on the stack using a push WAX? The byte that really matters is still at the same place. So that's why, in this case, it doesn't really matter. But what if you have a third argument after the character? Then it matters, because how many bytes you use up for the second argument will determine where the third argument starts. Is that making any sense? Okay, so if that is the question, which in your homework assignment is not a big deal, but in general it is a big deal. So since I have not really talked about this, when you have a character as a parameter, how do you push that argument? How do you find out, okay, if you're left on your own, how do you find out how many bytes a quote-unquote character type parameter is going to take up on the stack? How do you find that out? I know the answer already, but I want you guys to kind of think about this. Knowing what you already know about C, C++ programming, can you find that out? So what I'll do is I'm going to write a test program just to do this, okay? But I want you guys to kind of think along with me so that you can try to figure out the solution along with me as well. Okay, I'll just call this params.c, and I will write a test subroutine. It doesn't matter what it returns, so I would name the return type to be void. I'll just call this my test subroutine. How are you gonna, what is the minimal list of parameters to figure out, okay, if I have a char type parameter, how many bytes does it use up on the stack? What about this? Okay, this is my first parameter, but by itself it's not helping because I don't know where it ends. Now if I do a size of x, it will always say 1, but that may not be the number of bytes actually pushed on the stack. So what I need is something else. Okay, what is after this doesn't matter. Can be int, can be char, can be a void pointer, can be whatever. It really does not matter. So I'm just going to make this another char. Okay, and the subroutine is not going to do anything, but I cannot make it do. Well, maybe I can. Okay, so let me just try this first, because I want to make this program as minimal, as possible. And the two chars, I don't really care what I'm pushing on the stack. In this case, I'm pushing 2 null characters on the stack, because I just need to find out how many bytes they're taking up. And then we have a return 0. So I'm claiming this program is going to be enough to find out how many bytes are actually being used up on the stack for each char type parameters. So what is the next step to do this? Okay, obviously to compile the program, get into GDB. But once I'm getting into GDB, what am I going to do? We can use a stack pointer, but the stack pointer doesn't tell me everything that I need to know. Okay, actually, let me go back to this program because it might be helpful if we change these to be somewhat unique values, right? So let's make one, 5D. And we'll change the other one to be, I don't know, 2, 4, okay? So these are 2 distinct characters that I'm pushing on the stack. So when I look into the content of the stack, I can more easily identify, oh, this is the character that I just pushed on the stack, that's the character that I just push on the stack. Can anyone tell what is 5D? Which character is represented by ASCII 5D in hexadecimal? Well, that depends on how well you remember the ASCII table. I cannot remember either. So in the absence of remembering, in the absence of that, you can always just use quotes, okay? You can just quote, this is the @ symbol, and this is going to be lowercase x, okay? Close enough. Okay. GCC-G-O params.c and GDB params. Okay, so now we are in the debugger. Quite obviously, we want to set a breakpoint in test because that's the whole point of this exercise. Run the program. Now we are in test. What am I going to do? There's a very easy way to do this. Okay. And it has to do with the ampersand symbol in C++. What does it do? What does ampersand do as a unary operator? Address of. Now, how would I apply address of? There are only several things at this point that I can take the address of. I can take the address of test itself as a subroutine, which is not going to be helpful. So obviously the next thing I can do is to take the address of x and the address of y. Is that going to be helpful? Do you think that's going to be helpful?
Yes.
Okay, exactly. So we'll say print where is x as a parameter. Okay, this one is not that important by itself. The address of y is important. So what is it telling you? They're taking up 4 bytes. So even though x and y are just characters, which only takes up 1 byte, okay, the content only takes up 1 byte. But what you're pushing on the stack is actually pushing up 4 bytes. So why? Why do you think that is the case?
Why is it taking up 4 bytes?
Why is it taking up 4 bytes? The compiler would not waste memory space without a reason. So there is a reason behind why even a single character takes up 4 bytes on the stack as a parameter. What do you think is the reason?
Is it because with C you need to know what type it is?
Not really.
No.
It has to do with the natural width of the data bus. So remember, the instruction set we are using right now is the I386 instruction set, which means it is a 32-bit instruction set. Okay, what does that have anything to do with? Oh, I want to push everything as 4-byte things. What do you think? It's the full width of the data bus, exactly. But why is that important? Why is the alignment of items with 4-byte boundaries important in this case? Well, think about it this way. So let's erase this, and this time I'm just going to give you another picture, but this time these are all individual bytes. Okay, so these are all individual bytes, and we have I will identify the actual 4-byte boundaries. Okay, so this is one 4-byte boundary. 1, 2, 3, 4. 4-byte boundary. 1, 2, 3, 4. 4-byte boundary, and I'm just going to add one more byte over here. Okay. So with a 32-bit architecture, the data bus is 32-bit wide, which means with every single memory access, I can grab 32 bits or 4 bytes at the same time. Is that okay? Because that basically translates to, if you remember our toy architecture, it translates to the toy architecture having a data bus of 32-bit wide. Okay? But the instruction set is still byte addressable. In other words, even though memory is organized by 32-bit at a chunk in each chunk, the instruction set still gives me the ability to access just 1 byte out of these 4. Just 1 byte out of these 4, and just 1 byte out of those 4, which is okay. Okay, that by itself is not a problem. Now you think about, okay, if I can just push 1 byte on the stack, that means certain items will no longer be 4-byte aligned. Is that okay? Because you keep pushing 4 bytes, and then you have a 1 byte thing. The next 4-byte thing is going to span over a 4-byte boundary. Is that okay? Okay, so I'm just going to draw that here with a blue pen, and just say, okay, this is out of alignment. It's no longer falling on the boundary of a 4-byte thing. The question is, how many memory access do I need to grab this item?
2.
It would need 2 memory cycles, because the first memory cycle would only be grabbing these 3 bytes. And then I need a second memory cycle to grab the 4th byte. That is the reason why we want everything to be 4-byte aligned on the stack. Is that okay? It's for the sake of efficiency. Yep.
So if you are passing down 1-bit Boolean, it's going to take 4 bytes.
Yes. A single Boolean will take up 4 bytes. So it doesn't cost you anything extra to push a 32-bit integer on the stack, and then you can use bitwise operations to interpret the 32-bit integer as 32 Booleans.
Mm-hmm.
But the compiler doesn't do that automatically. In other words, if you have 32 Boolean parameters, the compiler doesn't understand and pack it into one single 32-bit word or 32-bit integer.
Mm-hmm.
So that's something it's just a limitation of what the compiler cannot do in this case. You can always use structs because with structs you can specify bit fields, and I think the compiler does pack bit fields within the structure. So there might be ways to pack things a little bit better, but in general you cannot depend on the compiler itself to do this packing. Okay, so are there any questions? So for your homework assignment, okay, let's go back to the homework assignment because all of this stuff here is to answer one single question in your homework assignment, which is how do I deal with this? And the answer is push 4 bytes. Okay, push 4 bytes where only the least significant byte has the character. The other 3 bytes, they don't even need to be initialized. Okay. Any questions about this part? No questions? All right. If there are no questions, I'm going to give you guys more examples today. And what you need to do is to look at all the sample code that I'm going through, analyze the program, break them into smaller pieces down to the mechanisms, and then you have to understand the mechanism and then utilize those mechanisms in your own homework assignment. Okay? All right. So let's go ahead and implement some of the string copy functions. Maybe string compare. Okay. So I'm going to implement my own string compare function, and I'll give you the C version first, and then we'll go ahead and implement it in assembly. This is string compare. Const char first string STR_A string A, const char STR_B string B. Okay, how many people know what is string compare and what it returns? Okay, and for those of you who may not have been exposed to this function, it's okay. We can easily look it up because string compare is one of the really standard C functions in C and C++. All right, so it compares the C string str1, okay, I use str_A in my case, but same thing, okay? String A to string B, or string 1 to string 2. The parameters, not really that important, but the return value is. The return value is going to be less than 0 if the first character that does not match has a lower value in string A than string B. The content of both strings are equal, will give you a 0 as a return value. And if the first string is greater than the second string, it will give you a value that is positive. Are there any questions about the string compare function itself? I can give you some examples. If I compare TAK, T-A-K, versus double quotes, versus T-A-K-E, take, if I pass TAK as the first string, take as the second string, what do you think string compare should return? A negative value, okay? So this should be less than 0 if I use it as string compare. Because this is a null character, this is a character E, right? The ASCII code of the null character is 0. The ASCII code of E is some positive number, so that's why TAK is considered less than take in this case. ABC versus ABC, they match exactly, so the return value is exactly 0. And we can now use an example of TAKE with an uppercase T versus TAKE take with an uppercase T. So in this case, it's going to be greater than 0, or positive, because lowercase t has an ASCII code that is greater than the ASCII code of uppercase T. Okay, so these are just examples to illustrate what kind of value is returned by string compare. Yep.
What if, like in the first example, the second string was much longer? Would it start comparing the rest of the characters
Nope.
in the string?
It will. It stops as soon as it finds a different character. Okay, so that's the key. Is if it will stop on the first character that is different, which will basically bring us back to the algorithm. Okay, so because the algorithm is relatively simple in this case, because how do you stay in the loop? You basically say, as long as everything is the same and it is not null. Because when you encounter null, even though both strings have a null, the null character is special because it's a terminator. So when you find a null character, you always exit the loop. Is that okay? So you basically say, if string A, or the pointer of string A, is not null, okay? Because if any one is null, you stop right away. And whatever string A points to does not exactly equal to whatever string B points to, stay in the loop. Because this means you cannot determine the order of the two strings just yet. Whatever you encounter up to this point are identical in both strings, and you have not seen the null terminator just yet. Does that make any sense? Why don't I have to check string B pointing to a null character? Why do I only need to check one? I mean, what if string A is pointing to a non-null character and string B points to a null character? Then is this condition going to handle that correctly?
Yeah.
Yes, because they wouldn't be equal in that case. Okay? Very good. So if I cannot determine the order between the two strings and I have not seen the null terminator yet, that means the only thing I can do is to increment both of these pointers so that I can move on and compare the next character from both strings. Now when I do exit from here, it means that one of two things have to be true. Either I have seen the null terminator of both strings because they're both the same string, they have the same characters, or I have found something that is different between the two. Does that make any sense? Okay. So let's think about this. If they're both null, then if I just return the subtraction of the characters pointed to by STRA and STRB, that would be the right result. If they are different, if I return the difference between whatever STRA points to and whatever STRB points to, would also still be the correct result. Because the subtraction between those two would still indicate either a negative number or a positive number. So that means the return value is really just the difference between the two, but you have to be careful about which one minus which one, and the correct order is STRA, or whatever STRA points to, minus whatever STRB points to, because in this case, if whatever STRA points to, the first string, is greater than the second string, it returns positive. If it is less than, it returns negative. If both of these are null, it returns 0. Is that okay so far? Okay. And I am going to have my main program here. I'm going to implement everything in C first, and then I'll convert this entire program into assembly. Not just one subroutine, but even main can turn into assembly. So pound include string.h to get the strings, and then pound include stdio because I intend to do some printfs and scanfs and stuff like that. Okay, so let's go ahead and do this. And you know what? I'm going to make this fancy, okay? Because I'm going to use command line options in this case. Does anyone know how to use command line options? Like, on the command line, you can say /main and then give it a whole bunch of stuff. Do you guys know how to do that?
Pass parameters into the
argc for the number of arguments. And we have const char double asterisk because it is an array of pointers. Or you can, if you want to look at it the other way, this will be fine as well. Okay. So the first thing I'm going to do is to say if argc is less than 3, then don't bother. Okay, printf need at least 2 arguments, and it will just exit. It won't do anything in this case. else, which means our argc is at least 3, then we have at least 2 strings to compare. What? 3? Why 3? Why not 2? Because the command itself, /main, is always the first argument. In other words, a command that you run through the command line always knows how you started the process, because the first argument is the command itself. So I'm not going to compare the command to anything. I will compare the other two. So that means I will say printf strcmp returns %d, which is the placeholder for the integer that is about to be printed. And the integer to be printed is strcmp, because I want to print the return value of string compare. And then we'll say argv bracket 1, the second argument, which is actually the first, well, the first string that I want to compare. This is the second string I want to compare, and that's it. So this is my little toy program, to test out the string compare subroutine, and it does not require GDB to work because it has printfs. It takes the input not from standard input file, but from the options of the command itself. Okay. Are there any questions about this particular program at this point? It's all good so far?
You said you could use the const char cc or star.
Yeah, because any array in C is really just a pointer.
Right.
So I could have done this, and it means exactly the same thing. So a pointer to a pointer can be seen as an array of pointers. And that's one of the things about C++ that is super confusing. gcc-g-o string compare.c. Wow, it actually compiled the first time. I was surprised, because this program has more than 4 lines, and if I don't make a syntax error in 4 lines, that's amazing. All right, so we'll just try out as string compare itself, and it comes back and complain and say, hey, you need to give me at least 2 arguments. Okay, fine. Let's try tag versus take. Okay. Oh, that's wrong. That is wrong because I forgot one thing. Well, maybe not. Okay, but it is wrong. Okay, so let's find out why it is wrong, because it's supposed to return what? Some kind of negative value. Okay, so it's not returning a negative value, and I have a suspicion that the loop did not work because I should not have that. Because I should say, while I'm not at the end of a string and both strings are matching up to this point, because the other one is saying while I'm seeing the null character and both strings are the same up to this point, which doesn't make any sense. So that's why, I kind of knew what it was doing, because it's returning a 0, right? So let's see how we can work this program backwards to debugging. Okay, when I make mistakes, it's great because I can now explain how to diagnose and how to debug the program, which I think is more important than anything else that you learn in college. Well, computer science classes. Okay, so we know it's returning a 0, and 0 is very difficult to be by accident. Okay, if it seems some gibberish value, yeah, maybe I'm not even having a return statement, so it takes whatever EAX has at that point as the return value. But it returned a 0. It printed a 0 here, which means whatever string A points to minus whatever string B points to is 0. Okay, they are the same thing. And then I go back and look at the loop and go like, well, that cannot happen if the loop does what it's supposed to. But the loop exit for sure, because if the loop did not exit, I would have an infinite loop and the program would not return anything. So the loop did exit. So let me just kind of unfix the program so that I can. Okay, so this is the program unfixed, which is wrong. So what are the 2 reasons for me to exit this loop here? Okay, the first reason is whatever STRA points to is not null. Okay, and guess what? it is not null to begin with. But why would it return a 0? Because both pointers will be pointing to, the first pointer points to uppercase T, the second pointer also points to uppercase T. Uppercase T is non-null, and that's why it got out of the loop. So that explains everything. But the flaw is basically the negation of the first argument where the cursor is on right now, because it is not supposed to be there. Because I have to stay in the loop if I do not see the null character, which means I have to confirm that whatever STRA points to is non-null. It is not 0 to do this. Okay, so that should fix the problem. GCC, and it returns minus blah blah blah. Okay, whatever the value it returns is not important. The fact that it is negative is all I need. So let's try out the second test case, which is ABC versus ABC. ABC returns a 0, and then the last one is lowercase take versus uppercase take, and it's 32. So it's working the way it's supposed to. What about empty string versus empty string? Should be 0, because it will be comparing the null character versus the null character. The loop would exit without a single iteration because the first character is the null character. Next question is, can we test it using this method to specify the null string? And the answer is yes, you can, because the double quote character on the command line can be used to enclose strings. So you can actually compare a null string versus a null string here. The next question now, for those of you who are thinking along the same line that I'm thinking, is then how do we compare double quote versus double quote? Because if double quote itself is used as delimiters of a string, then how do we indicate double quote itself as a part of a string?
Escape.
Escape, and how do you escape in general in C? Backslash. Very good. So we can compare your backslash, whoops. Well, it did compare in this, well, it did not compare in this case. So backslash quote versus backslash quote should be the same, but that's how you escape it. Is that okay? Now, how do I know this is escaping it the way it's supposed to? Okay, if I compare a single double quote as a string to the null string, what should be the difference? The difference should be the ASCII code of double quote itself, right? Okay, so when I press the enter key, it returns a particular number, which is 34 in this case, and 34 decimal should be the ASCII code of the double quote symbol. The question is that really the case? So we need to look up the ASCII table. I don't think I have the ASCII table man page installed for some reason, which is bugging me, but that's okay. We can always look up the ASCII table from the internet and locate the double quote or ASCII 34, and ASCII 34 turns out to be a double quote character. So I just confirmed what I suspected. Okay, double quote can be used to delimit a string on the command line, and backslash double quote is the way to escape a double quote. So you can actually specify a double quote in the string itself. Yep.
To that parameter into main, does it have to be that name of
the argument, the parameters, no. So if I look at what is it? String compare, string compare.c. So how you name the argument is not important, but the type is. Okay, so the first argument has to be of the type integer. The second one has to be of the type of pointer to a pointer of a character. Now, if you miss this const here, is not the end of the world, but you might end up, if you accidentally try to overwrite those strings, you can end up with a segmentation fault, because this part of memory may not be writable.
Okay.
Or at least you're not supposed to overwrite.
Okay.
Okay? Any other questions? Those are all very good questions. Well, I have a question. Are there any more hidden parameters of main? The answer is yes. because it also passes all the environment variables to the process. So if you set an environment variable, all of those things can be passed to the process as well. But we are not going to deal with that. Okay. Now I'm going to convert this entire program into assembly. Not just string compare, because that would be too easy, but I also want to convert main into assembly. Okay. So how would we do this? So I'm going to do this in two files in this case. So let me get out first, and then do -O so that we can split the screen. We'll go ahead and implement string compare first. Okay. Okay. So on the right-hand side, I'm going to write the code, the assembly code of string compare. The first thing I do is not to write the code at all. Okay. First thing we need to do is to export the label of the function itself so that the linker can see it. The second thing I will do is to name all the parameters and, if any, local variables. So I always start with old EBP. The displacement of where EBP points to is 0 when it comes to the old value of the frame pointer itself. Do we still remember this part? Okay, from Tuesday? Okay. The return address is the one thing after EBP. And then we have the two parameters. So in this case, STRA is right after, oops, +4. Okay, forget that. So string A is after return address, and at return address takes up 4 bytes on the stack. String B is the same way. Yep.
So if the EBP doesn't point, is it 0 because the old EBP doesn't point to anything, or?
No, it points to its own old value saved on the stack because of the push EBP instruction at the very beginning of the function.
Okay.
Okay. We don't have any local variables, so I'm not going to define any local variables. And then we can now actually start to write the subroutine. But this is how I write the subroutine. I always write the label and the return right away. Okay, because these two things are always necessary. Even if the function doesn't do a single thing, you still need these two things. And then I would write push EBP. Now, if I really want to be anal about this, I would do a pop EBP right away, because they are like parentheses. Okay, when you open a parenthesis, you always want to say, okay, let's write the close parenthesis, and then go back and fill in whatever is in between. This way, you don't forget. And then the next thing we do is to take a snapshot of the stack pointer so it becomes the current EBP. And that can be done with a single move instruction. Copy the stack pointer to the frame pointer. But the exit code is exactly the opposite of this, which is basically restoring the stack pointer from the frame pointer. Okay, so this is how I write the program. Okay, it's not sequential, even though I know this sequence of what we call the epilogue and the prologue of a subroutine. I still write code like this so that I don't forget. Okay. All right, so now we are in the actual subroutine here. I can use the parameter STRA and STRB throughout, but that's really cumbersome. And we do have enough registers so that we can use one register for one of the pointers and another register for the other pointer. EAX is kind of special because that's the return value, so I may not want to use EAX for this purpose. But I can use the other 2 registers, not 3. Because remember, EBX is special as well. Okay? If you mess around with EBX, you have to save and restore the value of EBX, because the caller of str's string compare or the caller of any subroutine assumes EBX is not changed. Okay? On the other hand, ECX and EDX can be changed by a subroutine. So I'm going to use ECX and EDX for this purpose. So first thing is to copy the parameters to those 2 registers. STRA is the displacement to the parameter STRA on the stack. It's a displacement from where EBP points to. So we have to use the based addressing mode, which is basically saying the location of the 4 bytes that I want to copy is where EBP points to, but not quite exactly where it points to. We have to add the displacement of STRA to EBP to get to that address. Okay. I will copy this to ECX and write a little comment and say ECX is STRA, or the pointer STRA in C code, and do the same thing with STRB, and that's going to be in EDX, so EDX is STRB. So that takes care of the initialization of the entire program, and now we can do the while loop. And since this is a while loop, we write the structure first. While begin, while end, and right before while end, we have an unconditional branch back to while begin. So this forms the basic control structure of a while loop. Then we have to decide how do we get out of the loop, okay? To stay in the loop, we have a conjunction, which means there are two reasons to get out of the loop. The first reason to get out of the loop is based on the compare instruction here, and we have to be careful to compare byte and not compare long, because STRA is a pointer to a character. So we are comparing character to character, not comparing 32-bit word to 32-bit word. So we're comparing byte. In this case, we're only comparing against 0, and it is whatever STRA points to. STRA is ECX, so that's how we do the compare. To stay in the loop, I want this to be non-zero, which means to get out of the loop, I want it to be a 0. Is that okay? But this is not the only reason to stay to be able to get out of the loop. So if this does not get us out of the loop, I have to do the second one. The second one, as much as I want to do it like this, I cannot. Why can't I do this? Because now we have more than one memory operands, which is too many, right? So we have to kind of go through a particular register. AL is fine, okay? So we have to move one of the bytes into AL, and then we can now compare byte AL with whatever the other pointer points to, like so, okay? And if I want to stay in the loop, they should be the same. If I want to get out of the loop, they do not want to be the same. So J and Z is the reason to get out. Yep, go ahead.
Which part of which register is AL?
It's part of EAX.
EAX.
Yeah. AL, AH are they form AX,
Yes,
and
that's
AX
higher
is a
level.
part of EAX.
But why exactly we're not? Isn't EAX still used for the return value?
Yeah.
But
Yeah,
you
we'll,
can
we'll,
use
we'll
this
deal
one.
with that later.
Okay.
Yeah, because we are not returning just yet.
Okay.
So before you get to the point where you are getting out of the subroutine, EAX is just one of the registers that you can use.
Okay.
Okay. All right. So if I'm not getting out because of either of these reasons, it's time to increment both pointers. So we'll go ahead and say add L $1 to ECX, which is STRA, add 1 to the other register, which is STRB, and we have the loop. Now when we get out of the loop, we have to specify the return value. So it seems to be pretty easy. Yeah, this is easy peasy, right? Because all we have to do is to say, oh, let's move byte EDX into AL, just like before. And the order of the subtraction is kind of important, because this time it is subtract byte. We are subtracting B from A, so we are subtracting AL. Oh, that won't work. So I have to make this ECX and then subtract, because I want the result to be in AL, so we have to, that's why I have to change this a little bit like that. Okay, are we done?
Isn't it going to return EAX?
Exactly. So we store the result in AL. In other words, if you look at AL as an 8-bit number, the sign of that number, or whether it's 0 or not, does indicate the correct result. But the return type of strcmp is not a char. Instead, it is an int, which is a problem, because it is now whoever is calling strcmp will look at the entire EAX and say that's the result. But the instruction that we have, like move byte and subtract byte, is only affecting the least significant 8 bits of the 32-bit register. Yep.
Oh, how do we know that AH is 0?
We don't know. We don't know what AH is. We don't even know
Is
what.
that okay if it's not?
It is
0?
not okay, so that's why we are not done yet.
Okay.
Okay, so if this is not, if we're not done yet, what am I gonna do? Yep.
Can I initialize the whole EAX before those 2 lines and that's it?
You can, but what are you gonna initialize it to?
0?
Then it won't take care of the case when it is negative. Let's think about this.
Okay, yeah, it will not.
Okay, but I do want to illustrate, what we're trying to deal with here. Maybe I can just use mouse pad on the screen to do this. Okay, so we have a somewhat of a problem. It's called sign extension. Okay, and there are usually instructions to do that. But in the absence of instructions to do it, can we do it with instructions that we already know? That's the question. Okay, because remember, this is not about learning, the 400 or 500 instructions of the instruction set. This is about problem solving. Okay, given the tools that we already have, can we solve this problem? All right. So the problem is this: -1 is represented in 8 bits. What is the representation of -1 using a signed 8-bit number?
All ones.
All ones. Okay, very good. 1 1 1 1 1 1 1 1. Good. Okay. What about -1 as a 16-bit signed number?
Also all ones.
But 16 ones in this case,
16
right?
ones.
Okay. So that means if you initialize a 16-bit register to all zeros, it's not going to work because it will only take, because if you initialize the 16-bit register to all zeros, then these will remain as zeros as you mess around with the least significant portion. Is that okay? So what we need to do in the code is not quite to do the subtraction yet. What we need to do is to first do a compare, so that we can find out, is it positive or is it negative? Because depending on whether it's positive or negative, we want to do different things. Is that making any sense?
Yeah.
Okay. So after the comparison, oh, by the way, is this a signed comparison or unsigned comparison?
Signed.
It is signed. Okay, very good. It is signed comparison. Well, it doesn't have to be, but it is. Okay, because your charts are signed to begin with. Okay, so with the signed comparison, we have JL, JG, JNL, JNG, and so on. So it doesn't really matter which one we use because it's just 2 kind of equal branches. So we just say JL to 1. So AL is less than EAX in this case. We go to, we are supposed to return a negative value, so negative value goes here. In this case, we are going to the positive value, which has to jump around the negative value thing so that we can get to the common point of return label. So, and by the way, return is not a reserved word in assembly, so we can use that label or use that name as a label. Okay. All right, so if it is not negative, it is positive. If it is positive, we're going to put what into EAX first?
Oh, zeros.
All zeros, correct. So move along all zeros into EAX, which will also destroy whatever it had before. So now we have to move byte again. That may be a better way to do this, but this will work too. And then this time we would actually do an actual subtraction. Let's see. Yep. Okay. So we can do it this way.
We don't have to move because compare doesn't mess up the AL. AL is still the same.
Hmm.
The compare
Yeah.
doesn't mess up the value.
The compare does not, but when I try to initialize all 32 bits, because you cannot isolate the most significant 16 bits of a 32-bit register.
Can we just move the initialization of EAX to 0 before even compare command? Just move it all the way up there. This way, AL will not be messed up, and all of the AH will be all 0 already and AL.
Well, but it won't handle the negative case. So you have to mess it up eventually. In one of the branches you have to. Do you see what I mean?
No, but right now it doesn't matter what AH. AH could be initialized to 0 even before we do anything.
Correct. But these two branches are now exactly the same because for the negative branch, I just moved -1 into the entire register EAX. So now I have 32 ones, right? So once we have all 32 ones here, then I need to do exactly the same thing as before. So these two instructions can stay the same after the two merges. That's all we need to do. Because all we need to do is to set up the most significant 24 bits, because the least significant 8 bits will still be done correctly using those two instructions. All right, are there any questions about this part? No questions? Okay, here comes the question. Should I go ahead and convert main into assembly first before we retest the whole program, or should I stop and just test string compare by itself? Yeah, we should stop the test. Yep. Okay, so let's see. So this means, when I need to comment out, well, actually I can comment out the entire thing. And this is a neat, easy way to comment out stuff. Remember, pound if 0, pound end if is, we're using the C preprocessor to comment out or to take a chunk of program out of the entire thing. And this time I can take out the prototype as well, because this prototype, as it turns out, is already in string.h. So I don't need to have a duplicate string compare prototype. All right, so let's give it a try. So we have the compile here. We just need to compile one more thing, which is strcmp.uppercase-s. Wow, no mistakes. Well, with all those lines, not a single mistake, not syntactical anyway. Let's rerun the program. Let's try that. It's all good. And that is good as well. So apparently the program is still working correctly. Let's try empty string versus empty string. That still works, so that's all good. Now how do we know it is actually using the assembly code and not continuing to use the C code? Because I could have made some stupid mistakes, so even though it looks like it should be using the assembly code, it can still be using the C code. Let me show you what kind of stupid mistakes can make that happen. Okay. Maybe this is the kind of stupid mistakes that only I will make. No, that's not it. Hold on a second. That doesn't look right.
Oh, main is string compare, right?
Oh, it's main. That's right. There we go. Okay, stupid mistakes. And I'm an expert on these things. What if this is a 1? Well, if this is a 1, it is not commented out. But it has to be combined with another stupid mistake. So if I turn this into a 1, because I forgot whether it should be a 1 or 0, and forgot to put in this dot global line, then it would be the same thing, okay? Because it would still be using the C definition, even though there is the assembly source file with the entire function. But because string compare from the assembly version is not exported to the linker would not have a problem and just automatically choose to use the C version. And here comes another even more stupider problem, okay? And trust me, I am the expert on these things. Even this would not use the assembly code. Why not?
I'm not going to see.
Because string compare is a standard C library function. In the absence of your definition of string compare, the linker gets smart and say, oh, I know where to find string compare from the library.
Wow.
Yep. So, but how do you confirm this sort of thing? Now, this time, it will not use my assembly definition because I commented out the .global line, which means the assembly code is not exporting string compare as a label. So as far as the linker is concerned, I use string compare in main, but I have no definition of string compare whatsoever from my own code, okay? All right, so in this case, how do you know that we have this problem? So we compile, everything looks good, okay? When you GDB string compare, you put a breakpoint. The first thing you probably notice is if you try to put a breakpoint on string compare, oh, it does use the one in the source file. Why would it know how to do that? Okay, let's run it. Okay, run it with 2 arguments, ABC and ABC. Okay, so it looks like it knows what to do, but it's not doing it. Because what it is complaining now, what is it saying? Breakpoint 1 is in, does this look like one of the files that I created? /lib/i386-linux-gdu.
No.
This is the library.
Yeah, can't you just remove the pound include for string cutting?
No, I cannot. Okay, let me show you why.
Defined how it's working.
But no, this is this line here. Okay, this part. It is only the job of the header file is to include the prototypes of string-related functions, but it does not contain the actual definitions. So if I remove this line, okay, so let's say I get rid of this line here, then the compiler will complain and say, I don't know what string compare is.
But didn't we define it though?
We lost both definitions. Because we lost the C definition because of the pound if 0 here, we lost the assembly definition because of .global being commented out.
Oh, okay.
Yep. Okay, so I just want to show you guys how to diagnose in case you suspect I may not be using the version that I've been working on. How do you, diagnose and figure out, okay, did I actually accidentally cause this problem? Okay, so now that this problem is resolved, we got 5 minutes, which I think maybe just enough time to do main. So I'm going to comment out main itself. And then I will go ahead and implement main itself in assembly. So I did this to main.uppercase s, which is fine because main is just a function. It's no more special than any other function that you write. Okay? All right. So let's go ahead and write main here. Main has 2 arguments, so we'll do the same thing here. Old EBP is 0, return address is old EBP plus 4. And then we have argc as the first argument, which is right after return address. And then we have argv being the second argument, and that is right after argc, just like that. So the arguments or the parameters of main do not receive any special attention. It is nothing more than just parameters. I do not have any local variables, but as far as the entry code and exit code is concerned, it should be the same. We take a snapshot of the stack pointer into the frame pointer, and then we reverse that when we are about to exit because we want to undo all the push and pops in between. Now we're into the actual body of the subroutine. We want to compare argc with 3 and see if it's less than. This is signed comparison. So we say compare long 3 with argc EBP because that's how we get to the parameter. If it is not less than, J and L, go to the else of the conditional statement. If it is, we will do something and then jump to the end of the if statement. So end if goes here. So you can see that I focus more on the structure of the control structure first before I actually put in the actual details of the control structure. Oh, we have a printf here. What do we do about the printf? Same thing, okay? The only difference is we need to define the string first. So what we need to do is to define the string, okay? So we say, I don't know, complaint here, okay? This is the complaint string, which is .askKeys, which has a null terminator all by itself. And then we can specify exactly what it is. Need at least 2 arguments, \n. And now we can do this, because what we can do is we can push the address of the string, which is complaint, okay, with a $, because we are pushing the definition of the label, not the first 4 bytes of the string on the stack, call printf. Printf is just a subroutine, no more special than string compare or any other function. When it returns, I am going to add 4 to the stack pointer to reclaim those 4 bytes. That's my then branch. The else branch is going to do, we have to push argv1 and argv2 on the stack first. Okay. We are running out of time, so I will do this in the short version. And this is called the based indexed addressing mode. Okay, so this is really rather fun.
Hurry!
Nope. I won't do it. Okay, we can do it like this. Okay, put a 1 into EAX, push L. Okay, this is the, that won't do it. That is not going to do it. Okay, move L, ARGV, EBP into A register first. I'll put it into register EAX. So EAX is now the address of the entire array. We want to get the content of the first one on the stack. So we will say push 4 indirect AAX EAX on the stack. So that's going to be the second item on the stack, which is a pointer. And then the second, oops, I got it wrong. Should be 8 because the push order is reversed. Okay. So we are pushing ARGV2 on the stack first, and then we have to push ARGV1 on the stack. So the second one is push L for EAX. Because remember, EAX is pointing to the array already. Having a 4 as the displacement means we want to access the second element of the array, but we are pushing the content of the second element of the array, which by itself is also a pointer. So we have both of these push on the stack. It's time to call string compare. And when string compare returns, we want to reclaim that part of the stack, which is adding 8 to ESP. And then we have to push EAX on the stack, because EAX is the return value of string compare, which turns out to be the second argument of printf. Okay, so we have to push that first, and then we have to push the second format string on the stack. So we just say format string. It is .ASCII. Okay, I'm just going to shortcut this to %d\n. So I don't want to use the time to type all that stuff. So push format string on the stack, call printf. When it returns, I always clean up the stack. This time we still have 8 bytes to clean up because we have 2 push long instructions. So we have to clean up those for 8 bytes. And that should be the end of this else branch. Okay? All right, I know this is a rush job, but we'll see whether it works or not. I'll be super amazed if this is working. Oh, at least it compiles. Okay, let's see. String compare, tag versus take. That's right. Okay. What about take versus tag? That's okay. That's good. That is good. Empty string versus empty string works too. Now, how do we know we are not accidentally using the C version of main? The C version of main has a longer statement to print. Okay, because I shortcut this in the assembly version because we are running out of time. So yes, you can say that I am super amazed that I did not make a stupid mistake with all that code. I would not try this, if I am actually doing the homework assignment. I'll see you guys at the lab if you have any questions about this. In fact, I'll move this into home folder so that it will stay.